Hello and welcome back to the course on deep learning. This is an additional tutorial to talk about the softmax and cross-entropy functions. It is not 100% necessary in order for you to go through all of the parts that we've been through in the main part of this section where we're talking about the convolutional neural networks, but at the same time I thought it would be a good addition to your bag of knowledge and skill set. So let's go ahead and dig into these functions. So to start off with, what we have here is the convolutional neural network that we built in the main part of the section, and then at the end it pops out some probabilities for 0.95 for a dog and 0.05 or 5% for a cat, given that photo in the left as an input. This is after the training has been conducted. This is actually it's running and it's classifying a certain image. And so the question here is, how come these two values add up to 1? Because as far as we know from everything that we've learned about artificial neural networks, there is nothing to say that these two final neurons are connected between each other. So how would they know what the value of how would each one of them know what the value of the other one is, and how would they know to add their values up to 1? Well, the answer is they wouldn't in the classic version of an artificial neural network. And the only way that they do is because we introduce a special function called the Softmax function in order to help us out with the situation. So normally what would happen is the dog and the cat neurons would have any kind of real values. They don't have to they don't have to add up to 1. But then we would apply the Softmax function, which is written up over there at the top, and that would bring these values to be between 0 and 1, and it would make them add up to 1. And to quote Wikipedia, the softmax function, or the normalized exponential function, is a generalization of the logistic function that quote-unquote squashes a k-dimensional vector of arbitrary real values to a k-dimensional vector of real values in the range of 0 to 1 that add up to 1. So basically, it does exactly what we want. It brings these values to be between 0 and 1 and makes sure that they add up to 1. And the way it works is that the way that this is possible is that because at the bottom over here you can see that there's a summation, so it takes the exponent and puts it in the power of z and adds it up, so z1, z2 across all of your classes, all of these values, and so that's your normalization happening right there. So that's how the softmax function works, and it makes sense to introduce the softmax function into convolutional neural networks, because how strange would it be if you had a possible classes of a dog and a cat, and for the dog class you had probability of 80%, and for the cat class you had a probability of 45%, right? It just doesn't make sense like that, and therefore it's much better when you introduce a softmax function, and that's what you will find happening most of the time in convolutional neural networks. Now, the other thing is that the softmax function comes hand in hand with something called the cross-entropy function, and it's a very handy thing for us. So let's first look at the formula. This is what the cross-entropy function looks like. We're actually going to be using a different calculation. We're going to be using this representation of the cross-entropy, but the result's basically the same. This is just easier to calculate. And what I know this might sound very unrelated to anything right now, just formulas on your screen, but there will be some additional recommended reading at the end of this section. So don't worry if you're not picking up on the math, like if we haven't explained the math right now. But the point here is that what is the cross-entropy? Well, a cross-entropy function, remember how we previously in artificial neural networks we had a function called the mean squared error function, which we used as the cost function for assessing our network performance, and our goal was to minimize the MSE in order to optimize our network performance. Well, that was our cost function then, and in convolutional neural networks we can still use MSE, but a better option in convolutional neural networks, after you apply the softmax function, turns out to be the cross-entropy function. And in convolutional neural networks, when you apply the cross-entropy function, it's not called the cost function anymore, it's called the loss function. And they're very similar, they're just little terminological differences and a bit different in what they mean. But for our purposes, it's pretty much the same thing. And what happens is the loss function is again something that we want to minimize in order to maximize the performance of our network. So let's have a look at a quick example on how this function can be applied. So let's say we've put an image of a dog into our network. The predicted value for dog is 0.9, and this is during the training, so we know the label that it is a dog. So the predicted value is 0.9, the predicted value for cat is 0.1. Then here we have the label, so we know it's a dog because this is training, and 1 for dog, 0 for cat. And so in this case, you need to plug these numbers into your formula for the cross entropy. So how you would do it is the values on the left go into the variable q, the one that is under the logarithm on the right side, and the values from the right would go into p. And so it's important to remember which one goes where, because if you get them wrong, you don't want to be taking a logarithm from a 0 value or a logarithm from a 1. So you just want to plug them in, make sure you plug them into the correct places, and then you basically add that up. So that's how the cross entropy works, and we'll look at actually right now we're just going to look at a specific step-by-step example of applying this function in real life, and it'll kind of make more sense what cross entropy is, and it'll be less like my goal in this tutorial is to make you more comfortable with cross entropy, because it can sound very convoluted and no pun intended. It can, like convolutional neural networks, it can sound very complex, right? Scary, but it's not. That's the point. So let's go ahead and apply it just so we know that it's not scary. So here's neural net, and also this will explain why we're doing this, why we're looking at different cost functions. So neural network 1, neural network 2. Let's say we have 2 neural networks, and then we pass an image of a dog. And we know that this is a dog and not a cat. And then we have another image of a cat, this time an animal, and it's a cat, not a dog. And here we have a weird looking animal, which is in fact a dog, not a cat, if you look very closely. So we want to see what our neural networks will predict. In the first case, neural network 1, 90% dog, 10% cat, correct. Neural network number 2, 60% dog, 40% cat, still correct. Worse, but correct. Second option, first neural network, 10% cat, dog, 90% cat, correct. Neural network number 2, 30% dog, 70% cat, worse, but still correct. And then finally, neural network 1 in image 3, neural network 1, 40% dog, 60% cat, incorrect. Neural network number 2, 10% dog, 90% cat, incorrect, and worse. So the key here is that even though both networks got it wrong in the last one, throughout all 3 images, neural network 1 was outperforming neural network 2. So even in the last case, it was very it gave dog like a 40% chance, as opposed to neural network 2 only gave dog a 10% chance. So neural network 1 is outperforming across the board when compared to neural network 2. And so now we're going to look at the functions that they can measure performance that we've kind of talked about already. So let's put these into a table. So there's neural network 1. You have the row number, so that's the image number. And then for image 1, you have what it predicted, 90% dog, 10% cat. So those are the hat variables. And then you have the actual values. So dog correct, cat incorrect. Same thing for image number 2, and same thing for image number 3. And same for neural network number 2. So dog 60%, cat 40% in the first image. That's what it predicted. The correct answer was dog, not a cat, and so on. And so now let's see what errors we can actually get. So what errors we can calculate to estimate the performance and monitor the performance of our networks. So one type of error is called the classification error. And that is basically just asking, did you get it right or not? Regardless of the probabilities, it's just, did you get it right or did you not get it right? So in both cases, for both neural networks, each of them, they got 1, or so this is how many they got wrong. So they got 1 out of 3 wrong. So 33% error rate for neural network 1 and 33% error rate for neural network 2. And so basically from this standpoint, both neural networks perform at the same level. But we know that's not true. We know that neural network 1 is outperforming neural network 2. That's why classification error is not a good measure, especially for the purposes of backpropagation. Mean squared error, different. And by the way, I did these calculations in Excel. I just didn't want to bore you with them, but you can totally just sit down and do them on a paper or in Excel. These are very straightforward calculations. Just basically take the sum of squared errors and then just take the average across your observations, and that's pretty much it. So for neural network 1, you get 25%. For neural network 2, you get 71% error rate. So as you can see, this one is more accurate. It's telling us that neural network 1 has a much lower error rate than neural network 2. And then cross entropy, again, we've seen the formula. You can also calculate this. This is actually even easier to calculate than the mean squared error. Cross entropy gives you 38% for neural network 1 and 1.06 for neural network 2. So you can see the results are a bit different when you look at them like that, when you look at the mean squared error and cross entropy. The question of why would you use cross entropy over mean squared error isn't just about the kind of like the numbers that they spit out. These calculations were just to show you that this is all, it's all doable. You can just do it on a paper. It's not, these are not very intense mathematics. These are pretty simple, straightforward things. But the question of why would you use cross entropy over mean squared error, it's a very, very good question to ask. I'm glad you asked it. The answer to that is, like, there's several advantages of cross entropy over mean squared error which are not obvious. And so I'll mention a couple, but then I'll let you know where you can find out more. So one of them is that if for instance you're at the very start of your backpropagation, your output value is very, 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 very tiny, very tiny. So it's much smaller than the actual value that you want. Then at the very start, the gradient in your gradient descent will be very, very low, and it won't be enough. It'll be very hard for the neural network to actually start doing something and start moving around and start adjusting those weights and start actually moving in the right direction. Whereas when you use something like the cross entropy, because it's got that logarithm in it, it actually helps the network assess even a small error like that and just do something about it. Here's how to think about it. So let's say, again, this is very intuitive approach. There's going to be a link to the mathematics, and you can derive these things through the mathematics in more detail. But a very intuitive approach. Let's say your outcome that you want is 1, and right now you are at 1 millionth of 1, right? 0.000001. And then you improve next time, you improve your outcome from 1 millionth to 1,000th. And in terms of, if you calculate the squared error, you're just subtracting one from the other, or basically in each case, you're calculating the square error, and you'll see that the squared errors, when you compare one case versus the other, it didn't change that much. You didn't improve your network that much when you're looking at the mean squared error. But if you're looking at the cross entropy, because you're taking a logarithm, and then you're comparing the two, dividing one by the other, you will see that you have actually improved your network significantly. So that jump from 1 millionth to 1,000th in mean squared error terms will be very low. It will be insignificant, and it won't guide your gradient boosting process or your backpropagation in the right direction. It will guide it in the right direction, but it'll be like a very slow guidance. It won't have enough power. Whereas if you do it through cross entropy will understand that, oh, even though these are very small adjustments that are just making a tiny change in absolute terms, in relative terms it's a huge improvement, and we are definitely going in the right direction. Let's keep going that way. So cross entropy will help your neural network get to the optimal state it's a better way for the neural network to get to an optimal state. But bear in mind that this only works when the cross entropy is only the preferred method only for classification. So if you're talking about things like regression, like which we had in artificial neural networks, then you would rather go with mean squared error, whereas cross entropy is better for classification. And again, it has to do with the fact that we're using softmax functions. So that's a kind of intuitive explanation of that. A good place to learn a bit more about that, if you're really interested in, why are we using cross entropy versus mean squared error, Google a video by Geoffrey Hinton called the Softmax output function. And he explains it very well. And, being the godfather of deep learning, who can explain it better anyway? And by the way, any video by Geoffrey Hinton is golden. He's just got a huge talent for explaining things. Anyway, so that's softmax versus cross entropy. I hope that gives you kind of like an intuitive understanding of what's going on here, but more importantly, that you're not put off by the term cross entropy, because Hadelin will mention it in the practical tutorials, and I wanted to make sure that you're prepared for that. And it's just another way of calculating your loss function and another way of optimizing your network, which is specifically tailored to classification problems and therefore convolutional neural networks, and comes in hand in hand with the softmax function. So, additional reading. If you'd like a light introduction into cross entropy, if you're interested in cross entropy a bit more, of course, a good article to check out is called A Friendly Introduction to Cross Entropy Loss by Rob DiPietro, 2016. Here's the link below. Very, very nice, very soft, no super complex math, good analogies, good examples. He uses analogies of cars, and you look at cars and talks about information and bits and restrictions, and how would you encode this, how would you encode that. It's a good article to have a look at, and will give you a good overview of cross entropy, like from an introductory standpoint. If you want to dig into the heavy math, like what you see here, then check out an article or a blog by How to Implement a Neural Network Intermezzo 2. So intermezzo is like an intermediary thing, like a intermittence in, like when you go to a theater and you have like a break between the first part and the second part. So that, because he's like going through all these steps, and then he says, oh, I got to explain this first. And yeah, so that's why it's called intermezzo. No other reason, as far as I understand. The article is by Peter Rowlands, 2016 as well. So both are quite recent. And yeah, check out this if you would like to dig into the mathematics behind cross entropy, behind softmax and cross entropy in this article, actually. So there we go. That's all there is to these two. Hopefully I was able to add some additional clarity, and good luck with that. It's going to be fun, and enjoy the practical tutorials. I'll see you next time. Until then, enjoy deep learning.